Okay, first, as you see, that's a definition about the lunar equation. Since we have a conformal mapping with the cut, so we have this is the standard form of lunar equation. It describes the mapping, the family of mapping FZT of the half plane onto simply connected domain with the cut. Lambda t, this is the control function of lunar equation. It's the pre-image of the movable end of the cut. Now we will talk a little bit about this control function. As you see here, this theorem, these two words here, they are saying about if we have a cut generating by lunar equation, as I mentioned before, number one, and this cut has, let's be sorry. The first theorem, if we have a cut generating by lunar equation and has an angle with a boundary, doesn't equal 0. The angle doesn't equal 0. So the control function in this case looks like the power series of t, and this series the power doesn't depend on the angle alpha. And these two words over there saying about that. So the second theorem is about if we have a cut generating by lunar equation, but this cut with 0 angle and has a tangent with the real line, the tangent with the order s plus 1 over s. So the expression of control function looks like equation number 2. As you see, the power depends on the tangent s, the order of the tangent s. The first article describes this general case, and the second one, Prokhorov and Vasilev, they describe when s equals 1. So they have the expansion power series of t with the power 1 over 3. If you plug s equals 1, you will find the expansion. So now my problem is to construct the conformal mapping, this figure in front of you, from the upper half plane into a polygon with a cut. This cut has a 0 angle, and the conjugate angle is alpha pi. So we construct the conformal mapping, and we will see the extension of control function. First we will write the lunar equation, and we will see the control function, how does it look, how the extension looks like, and we will see how is it going. This is the equivalent task for more accuracy. Just you see alpha pi. This is the polygon with the cut 0 angle with alpha pi, the conjugate angle alpha pi. The equivalence due to the fact that this family of regions is obtained by the linear transformation, fractional linear transformation of the previous region. And lunar equation is invariant with respect to fractional linear transformation. Now, here we go. We will first normalize the function f under this condition. The first condition, when z goes to infinity, we know that we fix that f infinity equals 0. So after normalization, we see that the function, the family of mapping looks like equation number 4. Is after integrating the square reducible formula number 3, we got number 4. As you see, the function over here is Gauss hypergeometric function. 2f capital 1 Gauss hypergeometric function. And the family satisfies lunar equation number 5. You see t over here. This t, this is not canonical parameter. Actually, this t is the distance between 0 and the movable end of the cut. So the lunar equation with our mapping satisfies is number 5, and the coefficient, the first coefficient 1 over 2c lambda 1 is easily found as equation number 6. We now have a system of differential equations to the parameters a and b. From relative calculation and simplification, we can find this system in front of you, and solving the system gives us equation number 7. It's b through a, and the constant c is the integration constant. We can find it from the condition, this condition. image fp plus r minus fp minus r equals minus h. After simplification, we can obtain that the constant c looks like equation number A. And we have lambda through A. From the normalization of the function, we can find that lambda is equal 1 plus alpha A plus B. So we have now lambda through A and we have B through A. And we can find A from the condition real f lambda equals T. From this condition, after simplification and substitution B and lambda, we can find equation number 10 to give us the parameter A. And the function after substituting B and lambda looks like this is the family of mapping after substitution. And this equation gives us A from such condition. Now we come to canonical parameter tau. So the family of mapping G denoted by letter G. Canonical parameter denoted by the letter tau. So the family of mapping, the Euler equation which our family is satisfied is this equation. As you see, it's matched with the standard form to the Euler equation with the initial condition. And the driving function of the Euler equation, lambda theta, has the expansion number 11. I will pay your attention about the power of our series. It depends on the angle alpha. As I said before, we will investigate the expansion and how does it look with the angle alpha, the conjugate angle alpha. So expansion number 11 is about the control function lambda, and the first coefficient lambda 0 it looks like that. We can easily find it. The canonical parameter tau is found as the equation down there. Now I will just present about the special case when alpha equals 0, the figure in front of you. Just to show, sometimes ago I considered this case. The function, the family of mapping fzt, and the parameters b, a, lambda, as the formulas over here. When we come to the canonical parameter tau, so the function g satisfies the Euler equation number 12, and as you see, we have the control function lambda as this formula. You see here we have root of tau. If you go back and substitute alpha equals 0 in our general expansion of lambda, you can find this equation, and the tau found by the formula tau. We have another particular case when alpha equal 1.5. It's just a particular case. The result is over there. The function fzt, the parameters b, lambda, a are given by the formula as 13. And when we come to the parameter tau, canonical parameter, we can find that it's satisfied by the Euler equation number 14, and the control function has this series. If you go back and go ahead, log alpha equals 1.5, you can find this series easily. The parameter tau looks like formula down there. As a conjecture, just for future, if we consider more difficult cases, more general cases, we're supposed to find the expansion of lambda. Control function lambda has the same expansion, number 11, as I mentioned before. And it's interesting to check the first coefficient lambda 0, as we did. That's all. Thank you all for your attention. Any questions, any comments? I'm all ears.
What is the motivation for such problem?
Motivation.
What is the motivation?
Let's say I will construct a conformal mapping, then we will check the Euler equation and how the control function looks like, the expression of control function, and how the conjugate angle alpha, how does it influence the expansion gamma to the control function. And we will later consider more cases, more general cases.
Еще вопрос. Если нет вопроса, давайте еще раз.